So Ex2D, question 4 to 6, more optimization problems, just setting up the formulas. Alright, question 4, find the area of the largest rectangular paddock. So it doesn't actually say the maximum area, find the maximum area, but that's what it's actually asking us for. Okay, the maximum area of the largest rectangular paddock. If you don't know what a paddock is, it's a place where we put cattle, like cows and sheep, that can be achieved with 400 meters of fencing. Okay, so 400 meters of fencing material. It's telling us something about the perimeter. Now let's define some variables. Before we do that, draw a little diagram. Here's my diagram of my rectangular paddock. Okay, give some dimensions to it. Let x be the length, let y be the width, and or let a be the area. What do I know about this rectangle? I know that its perimeter is 400 meters. I'll write a formula for my area. The area of that rectangle is xy. The perimeter of that rectangle is 2x plus 2y. I know that the perimeter is 400. I can now rearrange this to get one of these variables by itself and substitute into my area formula. So I'll rearrange. I'll take the 2x from both sides and then divide everything by 2. Y equals 200 minus x. Now I'm going to substitute in into this formula. A equals x 200 minus x. Use my different color. And then I can expand it to make it a little bit neater before I do my differentiation. 200x minus x squared. This will be a lot easier to differentiate than the first one. The first one we'd have to use product rule needlessly when we could have just expanded by ourselves. Okay, from there it'll optimize. Question 5 is a bit more interesting. So cylindrical cardboard postal tubes are made with the restriction that the sum of the length and the circular circumference are 120 centimeters. What should the dimensions be for maximum volume? I'm just going to change this question slightly so that I guess you're not confusing L's and H's all the way. I'm going to call this the height of the cylinder, because we know in our formulas for cylinders we always refer to the height. Okay, so what's the thing I'm trying to maximize or minimize here? What should the dimensions be for maximum volume? Okay, I'm trying to maximize the volume and I'm talking about the dimensions. Okay, the dimensions of a cylinder are typically the height, which we'll call h. They've drawn the diagram for us, and typically use the radius r. We could use the diameter, but all our surface area and the volume formulas refer to the radius, not the diameter. So be a good boy and define my variables. Let h be the height of the cylinder. Let r be the radius. Now I'm trying to find the maximum volume. Let v be the volume. Okay, so a formula for volume of a cylinder should be saying, yeah, I know that formula already. Volume of anything is the area of the base times the height. Okay, in this scenario, the area of my base is the area of a circle, which is 2 pi r. I should say no, it's pi r squared. Okay, area of base is pi r squared times the height. Okay, and since it's multipliers, we don't need to write the multiply sign between them, we can just put all the variables together. Okay, so I know my formula for volume is pi r squared h. Okay, if only I could optimize this already, but I can't because I've got r's and h's everywhere. Let me define some other relationship between them. Typically they'll give you some sort of like surface area, maximum surface area, so that you're really finding what's the biggest thing I can make with a certain amount of material. The one in this question is a bit weird. This restriction that the sum of the height and the circular circumference is 120 centimeters. So what that information is really telling us is that the height plus the circumference of this circle, which is 2 pi r, has to equal 120 centimeters. Alright, hopefully when you look at this, you think, okay, now I've got some information that relates h and r together, I'll be able to substitute it into my formula for volume. Again, we've got two options. We can try and substitute for r or for h. Hopefully you can see that rearranging this for h is going to make it a pretty easy substitution. So if I rearrange for r instead, I would be substituting this into r, and I'd have to square it and it'd get really messy. Okay, so from here, substitute h equals 120 minus 2 pi r into v equals pi squared h. V equals okay, some dude wanted to knock on my door, so I had to stop that momentarily. But that's okay. So I was substituting this h value into my formula, so this part going in to where h is. So pi r squared h, so 120 minus 2 pi r is going in there. And then I can do some expansions. So this will be 120 pi r squared. I put the number at the front, then the pi, then the r squared. And we'll be subtracting 2 pi squared r cubed. Okay, since it's probably the first time you've differentiated something like this with pi in it, when I differentiate it, I'll get 240 pi, so I've multiplied 120 pi by 2, and then reduced the power of r by 1. Then I'll do a similar thing here, minus multiply by 3, so I now have 6 pi squared, multiplied by r, with the power reduced by 1. Okay, you should be able to solve this when you set it equal to 0. You should be able to do the factorization yourself. You're saying, okay, there's a common factor of r, and then left over is 240 pi minus 6 pi squared r. So either r equals 0 or 240 pi minus 6 pi r squared, so 6 pi squared r equals 0. And you should be able to solve this in a reasonably straightforward fashion. Yeah, that shouldn't be too big of a deal. Don't get afraid just because there's some pi's around the place. Okay, question 6 is another sort of area volume problem. We've got frame of a container in the shape of a cuboid. Okay, cuboid just talking about like a rectangular based prism. Shown at the right. It's to be made with a total length of 18 meters of steel, edging. Okay, so we've only got the frame. So even though how this is drawn, it looks like it's a box, okay, there's only material in here. If I wanted to, I could come along here and walk all the way through here, okay, walk inside the frame, and then walk outside here. Okay, there's no walls on that box. Okay, so again, there's all of these different parts to it. You'll never be given these parts in a question in an exam. Okay, you'd probably just be given part C and D. Okay, if it's to be made with a total length of 18 meters of steel, find the length of each edge for the maximum volume. Okay, trying to optimize volume. Alright, so I'll define some variables. They've already done it for me, which is a bit annoying, but that's okay. We'll let the I guess I call that the length, the x. I'll let the width be 2x. Yeah, I probably should have named them differently. I'll call this the depth. And we'll call this the height. And let the length be L. Okay, it doesn't really matter how we name these, it will all sort itself out in the wash. And I'm trying to find the maximum volume, so let the volume be V. Is that the way I normally write it? No. Okay, so it should be the other way around. Let x be depth, let 2x be height, but it doesn't matter too much. Trying to find maximum volume. Volume of a box like this is length times width times height. Okay, I'll just call this width then, to be consistent with my formula. Find a volume of this thing. I can write the normal formula here if I want, okay, but I know that I'm really after these three things multiplied together. So x times 2x times L. Okay, or I can write it as 2x squared L. I'm trying to find the maximum volume that I can make with my 18 meters of steel. I've got x's and l's in here. I can only have one variable, so I'm going to try and find this relationship. Length of steel is 18 meters. So let's have a look at how much steel we actually need for this box in terms of x's and 2x's and l's. So I'm just going to look at how many ones have the length x. So I've got 1, 2, 3, 4 of these. Okay, so that 18 meters is going to be made up of 4x. We've done them. What about the vertical ones? So I've got 1, 2, 3, 4 vertical ones. Okay, so plus 4 lots of 2x. And then I'll look at these ones sort of going back. I've got 1, 2, 3, 4 of these. Okay, so plus 4 lots of L. I've got this relationship now between x and L, a really colourful one. I'm going to rearrange this to get L by itself. I'll do some expansion first. 4x plus 8x plus 4L. I'll collect some like terms. I'll get my 12x to the other side. So 18 minus 12x equals 4L. And then I'll divide everything by 4. Okay, so L will be 18 minus 12x all over 4. There's not much I can really do here for the L. In most scenarios, if it was instead 20 minus 12x on 4, I could divide both ones by 4 and have 5 minus 3x. I can't do this here because I've got this 18 on 4 out here. Okay, but this expression for L, which is actually the answer for part A, is going to get substituted into here. Okay, so I'm going to sub L equals 18 minus 12x on 4 into V equals 2x squared L, and see what happens. So V equals 2x squared times 18 minus 12x on 4. Okay, that's my function done. It's really ready to differentiate now. I can do some simplifications though before I start differentiating. So I'm multiplying one thing by a fraction. I can imagine that this is divided by 1. Okay, and multiply the two top lines. So it'll be 2x squared 18 minus 12x divided by 1 times 4, which is 4. Okay, and from here I'll be able to do some cancellations here, and I'll be able to do some expansion on the top line. Let me do this. I'll do it up here. So I'll expand the top line. I've got 18 x squared minus 12x cubed. That's all divided by 2. And now I can do this nice thing where I divide everything on the top line by 2. Okay, so I get 9x squared minus 6x cubed. Okay, and that's the function that I'll then be able to differentiate pretty easily. If you don't really know what happened in these two steps, maybe you'd be more comfortable taking out a common factor of 2 on the top line. So 9x squared minus 6x cubed on 2. And then you can cancel those two and we'll still get that same result. Okay, whatever works for you.